can't graph it, right?
Not to begin with. You could have graphed to check afterwards, though.
I know that process. I just didn't know that was
All right, let me grab everyone's attention back. Really quickly. Let's really quickly take a time out and consider how this can go better on another day. Ready? The first thing I told you was opener. Some of you didn't know where to go. Do you know where to go now?
Yes.
Second of all, I told you guys to write down the problem. Hopefully that was pretty self-explanatory. And then I told you how you should problem solve through this or any opener that you might have. As you read this opener, cool kids, it's not going to work today, is it? Okay. I apologize. Give me just 1 second. We're going back to the opener, which is right here. Okay, as you read, what are the two pieces of the directions that you should have zoned in on, that you should have zeroed in on, that you should have been like, ooh, that's important from the notes? Okay, the x-intercept and the y-intercept. If you did not know off the top of your head what to do, the answer was not to go to your calculator yet, although I did say at the end you could have checked in the calculator. The answer was not to go to your calculator yet. The answer was to pause and think, what is an x-intercept and what is a y-intercept before you do anything else. Okay, volunteers, 2 different volunteers. Actually, just one. What's the x-intercept, y-intercept? Go ahead, Mike.
Isn't the x-intercept where the line goes to the x-axis?
Pause. It's not a line. So instead, just generalize how you describe it. The function, the graph, the curve, something like that. But yes, it's where it goes through what again?
The x-axis.
Good. For the x-intercept, it's where it hits or crosses through the x-axis, and then similarly, the y-intercept is where the function goes to the y-axis. Okay. So then, you should have at least somewhat tied that, especially if you started homework like you were supposed to reinforce what we did yesterday. You should have said, oh, wait a minute, there's something special about those 2 points. And if you could not remember what that something special was, even if you thought about the graph and thought, if it's on the x-axis, what do I know? I know something. I'm supposed to plug in something. I told you, if you're stuck, what were you supposed to do? Look at your notes, and specifically probably right near where we left off. What were the problem-solving steps, procedures, clues as to how to find an x-intercept algebraically, not with a graph, because I said try it by hand. What did it say, guys? For the x-intercept, yes, we do need to set y equal to 0. X-intercept, set y equal to 0. For the y-intercept, what do we do? These are 2 separate things to do. 2 separate characteristics that we're solving for. So, should you, if you had gone to your notes and found where x and y intercepts, hey look, that's the title, right? Found where the intercepts were, should you have at least known from your previous experience in math, oh, take out the y, put in a 0. Take out the x, put in a 0. Okay, which one's easier to solve? The top or the bottom? Oh, definitely. And that's what I said yesterday. Totally agree with that. The y is so much easier to solve. The x is definitely harder, especially in this one. So, if you wanted to, could you have started with the y-intercept so you would at least get part of the problem done?
Yeah.
Okay. So for the y-intercept, those of you guys that were able to do this, which hopefully was everyone, because all of us took the same notes yesterday. If you were absent, of course, maybe you need another day to catch up. The video is online. But when you plugged in, guys, what did you get for setting x equal to 0 and simplifying? Yeah, most of you didn't even need to write all this out because isn't there 0 minus 0 minus 0? So what's the end of the day? What is my y?
0.
What is my point? The y-intercept, 0, 0. Following the y-intercept procedure, setting x equal to 0 and simplifying. X is 0. Automatically, we knew that. We plugged it in. Y is 0 is what we solved for. Y-intercept is done. What's our next job? The x-intercept. What do we set equal to 0 for the x-intercept? Y as in porque, por qua. Why is this one a little bit harder than the other one? You need to do math. Yeah, specifically algebra. You need to get x alone. And right now I have x in 3 different places raised to 3 different powers. What should you guys have thought of that I didn't explicitly write down, but I did put it and I explain it when I put down algebraic in the parentheses as to how to solve in your notes. Factor. Explicit factor. So, some of you right away got stuck because you're like, it's a cubic function? You're mean. Except, why is that actually really, really nice on this one? Greatest common factor, why not pull out the common x? Then you did an x squared minus 4x minus 21. Now you're like, oh, you're mean, it's a trinomial. Except that was actually really nice. Is there a number in front? No, it was weird. Isn't that what you guys really hate? Number in front. Okay, so you didn't have to worry about the number in front. Instead, you just had to think about what factors of 21, right, add to be negative 4. If you did the x method ever in your past, you're thinking what factors break 21 down into 1 and 21? Nah. What else is there? 3 and 7. I need a negative.
Negative 7.
Exactly, because I need to make these add to negative 4. Bingo. With an easy factoring problem where there is no number in front, how would I finish my factoring with these pieces I just found? X plus 3. Good. Make one of them x plus 3 and make the other one. Give me a quick little thumbs up, not like huge flashing in the air. This is somewhat like, oh, we've learned this. Some of you just don't participate. I hope. None of us can say that this is completely foreign or new. Question. How do I find the zeros? And I apologize, it is getting small. Most of us don't need the top of the screen anymore. How do I find the zeros when I have an expression fully factored? You guys have been answering a lot. Come on, someone here. How do I find the zeros? Yeah, there we go. I don't know why that told me that. Jaden, go ahead.
X plus 3 equal to 0.
Perfect.
X minus 7 equal to 0.
Perfect. Don't forget the other one.
X is just the 3.
Take each and every factor. 7 equals 0. Right? Now, do most of us need to write that? Probably not, but I need you guys to realize and not forget there are truly 3. Well, I like to write them in numeric order. So I would do negative 3, 0, and 7. Same thing as 0, negative 3, and 7. But I need you to realize there are 3 answers, not just 1. Those are the x values, so how am I going to answer the final question of what are my x-intercepts? I know the x and I know the y because the y was 0, right?
Yeah.
I know the x, I know the y because the y was 0, I know the x, the y, because the y was 0. Real quick, in a humble but honest, being real way, how many of you guys got all of the answers for the x and y intercepts before I did them? Cool. How many of you guys got at least half of them, you would say? Cool. The rest of you guys, do you have any questions for me? Are there, for those of you that started, which should be everyone, their homework last night. Hey, I can even spot check and start. You know that? That's pretty cool. But we didn't open her today, so I probably won't. Just letting you know. Just letting you know. I could spot the start, right? Because that was homework. So I could walk around the room right now and give points if you started.
Awesome. I wrote it down.
Just letting you know. Time out. That was what we call a warning. A teaching opportunity. Just something to be aware of. Coming back. For those of you that started homework, are you asked to find x and y intercepts with graphs?
Yes.
Sometimes. With equations. Sometimes. So, just be ready. Okay? We have one more huge topic to go over today. So, composition books, if they're not out already, go ahead and put the spiral away. And those of you that did not have homework started today, say a quick little... Not making okay, so just what symmetry? It's hard. Symmetry's hard. Not impossible. And we're going to actually introduce symmetry today in one way. In a future section, we'll talk about even and odd symmetry, which actually they go very, very closely together, actually exactly together. Or we're talking about functions. So don't worry, today is not the only day that we're going to talk about symmetry. Still in 1.2, you guys can kind of tell a couple different ways. Number one, there is no new section or title, right? Number two, homework wasn't due yet, which means we're still finishing. And number three, Backboard says we're starting in 1.2. Is that cool? Just getting us all oriented so we know how to kind of be independent. Why do you think I want you guys to be working to be independent? Not meaning you don't need me, but like you can do things on your own.
Roll up.
Yeah, you're kind of getting to that place where you're supposed to be doing things kind of on your own. And you guys love it when it means like freedom, but when it comes to like doing work on your own. So we got to make sure that as we grow, as we're maturing, if we want independence in one area, we need to show responsibility in our independence in other areas. Does that kind of make sense? Like how conversations with parents go really well if you have some evidence as to how you can handle the freedom. Anyway, if I were you guys, I would skip maybe one line in between each. Give you a second to get set up. How many parents are coming tonight? Who do I get to meet? Excited? Really quickly, can I see hands of those who were absent yesterday? Those were kind of like our first absences, I think. Well, this week. Like last week, people were joining the class, and there was Benson came late. Well, actually, he transferred to me. Yeah, he's transferred. Okay. But we had some weird like people come in and out of the way. So with absences, real quick, just because both people who were absent asked me questions today, just made me know that we don't really talk about it too much. What do I do in class? What's the little like red circle in the corner? What's going on?
Recording.
Recording. Right. So I record every day's lecture, and as long as technology allows, and I haven't been going literally nonstop all day long, which sometimes happens, literally from like 7 in the morning till about 5 or 6 at night. There are kids who are asking me questions. If that doesn't happen, I usually get the video loaded by probably 3:30ish. And it'll be online. How do you access that video? Because it shows you what we did in class, whether we graded homework, whether I talked about logistics. Yesterday was an important day as far as logistics, so I'm asking those people who are gone. I already talked to both of them, but I'm asking them to watch the video. We talked about homework grading and color pens and how to be ready with the day a homework assignment is due and how do I grade it and all that stuff. But where do I find that video? You guys know where I am, right? Cool. Right here. The video is my YouTube channel. But if you want to get to class notes, like the PDF version, you just want to copy it really fast. Yes, you can go to class notes, but as I've said before, just bookmark the class folder because I have everything waiting for you as far as your homework sheets, the problems you're supposed to do. Obviously, the exercises come from your book, as well as the class notes, and it's just an updated file. I just keep all the notes in one file, chapter 1 notes. It takes forever to load because my computer is slow. There you go. But those of you that were gone, you can access the PDF right here, but you miss all of the extra how to grade homework, etc. And as we talked about yesterday, do I give you points for grading your homework every day that it's due? Yes. So if you don't do it, do I take off points? And the answer is yes. So those of you that were absent, sadly, you missed the whole talk about what to do if you're absent with the homework, but it's on the video. P.S. Is there ever any like downtime that maybe you'll go faster than I will in a video? You're like, this is going to waste so much time that I have to watch a whole class period that you actually miss, so you're making up. It kind of makes sense. How can you speed things up on YouTube? Little setting wheel, right? Click it, make it 1.5, maybe even 2. My not be good if I'm talking, because I kind of talk fast sometimes anyway. But could it be good if there's like dead time? Like, okay, I'm just going to speed it up real fast and I'll pay attention when she comes back. Does that make sense? It's a great idea. All right, cool kids. Here we go. Symmetry. Let's get a picture for each, because I don't know if you guys are visual, but I am sometimes. I like visual and auditory. That was a question on the elective you're going, right? Kind of like if you're identifying one learning type other than over and above another. I'm going to show pictures for each of the symmetries to give us a quick idea right after Chris. Go ahead.
Oh, I just have a question about the notes. I just wanted to make sure. Do we start a new page every day?
Every section.
Every section.
Every
Okay,
section.
thank you.
Because I only have you start a new page for sake of organization. I don't really grade based on days, I grade based on sections. However, if you have like a little blip for a section, and I know it was more like a I'll get some points off. So make sure you have it in its entirety by grade by section. X-axis symmetry. What I want you guys to think about with each three of these names, and maybe you've heard this before, but I want you guys to think about how to fold a piece of paper. Question. Why or how do butterflies have symmetry? Why or how? What's an easy way? If you were to talk to a little elementary kid, like a second grader, they had just learned the word symmetry, and they learned that butterflies had symmetry. Question. How would you describe it? Michael.
If you fold the butterfly in half, and it's the same.
Basically, if you fold the butterfly in half, would one side look like the other? Would they basically, right? Would they basically outline each other? Yes. Okay. So if I have a piece of paper, this is horizontal, so we're going to call this which axis? Axis, the X. And then this one's going to be vertical. So this one's going to be my Y. Okay. Let's go ahead and label our quadrants. And you guys don't need to do this. I'll do this. Should have already marked it. That was pretty good. Okay, we have an X, we have a Y. Let me label my quadrants so we can be oriented. There's quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Okay. I have my quadrants, true? Okay. If a graph, when I fold along the x-axis, would copy one side and the other. If a graph, when I fold along the x-axis, would copy one side and the other, it has x-axis symmetry. So, if I was to give you, for instance, this graph right here, the sideways parabola, maybe even shifted to the right somewhat, then that was a perfect parabola. And parabolas are very rarely perfect. But that was a perfect parabola. Question, what's going to happen as I fold?
Will change direction.
If I fold it along the x, right? Here's my parabola right here. If I fold along the x, are they going to be on the same place? Yes. Right? Now, what if I was to fold that one along the y?
Then it changes.
It's not there, right? If I fold along the y, it's not on the other side. So it has x-axis symmetry, because if I fold along the x, yes, they're going to meet, like a butterfly, true? I'm going to give you a quick illustration as to what this graph could be. Let's see, this would probably be something like x minus 2 equals y squared. I'll make it somewhat precise. There's 1, there's 2. The y is squared. We don't see it very often, and actually it's not even a function. If you guys remember, it fails the vertical line test. That's for another day. Y-axis symmetry. What would be an example of a graph such that if I folded along the y, they would match up? Yeah, just a normal one, right? You could heard it from the back. What if I was to give you just a normal parabola? Just a normal y equals x squared. If I fold it along, it could even be shifted up if you want, but for sake of illustration. Who are you? Oh, hey, look, I had a hidden one. I forgot. That was probably from like 3 years ago when I tried to make the smart boards really cool. Anyway, who's that organized? Not me. Look, he's gone. Okay, so if I fold along the y-axis, do they copy for that one? Yeah, he has y-axis symmetry. Origin is the weird one. Origin says, basically, if there's something in the first quadrant, if I fold over, it's not there. But if I fold over and down, it's there. Let me give you an example. It's not just folding over, but it's folding over and down. If I fold over and down, it's there. Similarly, if it's something in the second quadrant, if you fold over and down, it would copy in the fourth quadrant. So if I fold over and down, it's there. An easy illustration for this one would be something like y equals, so something like 1/4 x cubed. If you put a nice little fraction, it kind of makes it level for a while. So that looks a little more like that one. So that makes sense how the folding kind of works as far as the names? X-axis, if you fold it, the top part, it'll copy. If you fold the bottom part, it'll copy on top. Y-axis symmetry, if you fold across the Y, what's on the right will be on the left, what's on the left will be on the right. And origin, what's in the first will be in the third, and what's in the second will similarly be in the fourth. Or vice versa, what's in the third will be in the first, what's in the fourth will be in the second. Okay, but let's go ahead and talk about the little clues that go along with it. Let's talk about the clues that go along with it. I'm going to show you an illustration on the next page as far as how to use these clues. But the key is, for each of these, the key is the second point that is also on the graph. The key is the second point that is also on the graph. Now you guys might have used your blank space, your blank line that you skipped for the graphs. That's totally okay. You might not have. You might have just drawn it next to the functions themselves. I'm going to put one little other characteristic, and that's what I meant the skip line to be for. You are going to plug in the point x negative y. And when you plug in, for the x-axis symmetry, when you plug in x negative y, it should simplify to the original. What I mean by original is I mean the original equation. If you plug x negative y into the function, and if you simplify, plugging in, make sure you simplify and make sure you plug in. Those are your two action steps. I guess I can put a semicolon, that would make more sense. Now, if it simplifies to anything other than the original, anything different than the original, it does not have x-axis symmetry. X-axis symmetry only occurs when you plug in x negative y, and it does indeed simplify to the original. And guys, basically that's going to be the same for the other three, or the other two, I should say. Every time you are plugging in, that's your first action step. Wherever that special point is. Now I'll illustrate really quickly why the special point is what it is for those of you that care. But you're plugging in that variation, that other point. And if that other point shows up, if that other point works, which the way that you'll see it works is that after you simplify, you are back at the original equation. It has not changed the equation. Then that symmetry is present in that function. Okay. Now, when we get into another type of notation, once we start talking about functions and f of x notation and all of that jazz, there will be another way of talking about how to find symmetry. It's probably the one that a lot of you guys were thinking when I heard just a few of you say, like plugging in negative x. It has to do with that notation. So there are a few other ways of thinking about symmetry. But this is what you can use in this section, before we talk about function notation and all that jazz. Let me quickly just show you why this is what it is. If both these points are on the graph, a given xy and the same x and the opposite y, it makes sense, hopefully, or for those of you that are visual, it might make sense, because think about, pick some random point on the curve, okay? This would have an x of approximately, I don't know, 3, and a y of, well, I don't know. If I plugged in over here, it'd be 3, 1. So if I have 3 and if I have 1, my question is, well, if 3, 1 is on the graph, what else should be on the graph? 3, negative 1. Does that make sense? If 3, 1 is on the graph with x-axis symmetry, 3, negative 1 is also going to be on the graph. Does that make sense? Yeah, because if it's up, it's going to be down. That's x-axis symmetry. This one, y-axis symmetry, if I have the graph, or the point, 1, 1, according to my clue, if it has y-axis symmetry, if 1, 1 is on the graph, what else is on the graph? So if I go up, right 1, up 1, I'm also going to go left 1, up 1? Yeah, that's the symmetry. If it's on the right, it's on the left. And last but not least, if I have the point 2 and, it'd be 2, 2, right? Because that'd be 8 over 4. If I have the graph, or the point, I should say, 2, 2, which is on the function, according to this, what else should be on the graph? And that makes sense. Because if I go right 2, up 2, I'm going to go left 2, down 2 because of the symmetry. So, hopefully these ones make sense. If you give like a specific example and look at it, you're like, okay, yeah. So if it's up, x positive y is going to be down, x negative y. If it's to the right, x, y, it's going to be to the left, negative x, y. And if it's to the right and up, it's going to be to the left and down, x, y. It's going to be negative x, negative y. Let's go ahead and go check out an example. Now guys, this whole table is in the book, and it literally tells you in order to figure out if the graph of an equation is symmetric with respect to, you need to replace y with negative y, and it should yield an equivalent equation. I've summarized that in the page before, but it is a little bit better fleshed out in the table. I just didn't want to make you guys write tons and tons and tons, so I'm saying plug in instead of replacing and yielding. I'm saying when you plug in, it should stay the same. But I am going to illustrate this 2 different ways. You can try to figure this out in a general sense, just using x's and y's. Or if your brain is a little bit more concrete, a little bit less abstract, you can find a specific point and test these different variations to see which other ones also work. Now, our goal is eventually, and for some of you, you can do it right now, to visualize the graph and not even need to worry about the plugging in. But I am warning you that we will get to a place where we need to find symmetries of functions that are far more complicated. And so if we're practicing the algebraic way without the graph, and I'll quickly peek at the graph and make sure that it makes sense. So let me illustrate this to you if that's okay. You guys are getting down what type of symmetries does the following display. We're trying to not think about the graph. Although some of you could be like, oh, hey, it's this guy shifted this way. I think he has this kind of symmetry. That's good. But show it algebraically as to how it's true. And to do that, I'm going to go ahead and write down the equation we're supposed to think about for the normal point. For it's x-axis symmetry first. X and then negative y. Negative x and y. Negative x and y. Those are the 4 different variations. X, y is just the normal point. And then 3 different variations, or the 3 different transformations. And remember, our goal is to see which of them, in general, which of them stay the same. So we know what the equation is supposed to look like with a normal x, y. You just steal the original equation and say, okay, I'm comparing to y equals x squared minus 4. I'm comparing to that one. To figure out this guy's symmetries, I'm going to plug in each of those different variations, and I'm going to say which one or ones, there might be more than one type, will simplify back to be the original. Okay? So, if I plug in a negative y, it just goes in the y spot, right? X stays the same. My question to you is it the same as the original or different? Different. Can I simplify it to make it the same? I could move the negative, but won't mess that side up. This graph does not have x-axis symmetry. Doesn't simplify to be the same. So your guys' turn, plug in the next one. This time y stays the same. X becomes opposite. Okay, I can do 8 minutes. 7. Alright. Hopefully you guys kept wising. Hopefully you plugged in negative x. Hopefully you plugged it in with parentheses, or else everything might have gotten messed up. Does it look different than the original? And the answer is yes. There's a negative x in there. But my question is, does it simplify to be the same? And your answer should be yes, because a negative times a negative is a positive. So does the function, when you plug in negative x, negative y, simplify to be the same? And the answer is yes. What type of symmetry is that? Worse comes to worse. Yeah, you have an x, you have a y, and then you also have a negative x with the exact same y. Oh, hey, that's the y-axis symmetry. So this one's a check, this one is a good. So for my graph from this, does have y-axis symmetry. We're going to see if there's anything else. Let's check the fourth one. When you guys plug in an opposite y and an opposite x, does it simplify? And the answer is yes. But does it simplify to be the same?
No.
No, because even though the right-hand side will go back to the original, does the y? So therefore, does it have origin symmetry? No. So our final conclusion is y-axis symmetry alone. But for just a few of you, because of the way your brain works, this other way of finding symmetry might be a little bit nicer. The dilemma is, in order to be specific and not to be general, you have to find a specific point first. So, can anyone tell me any point that is on this curve? Pause. That does not have an x or y as 0. It has to be in a quadrant. No x or y can be 0. Ooh, how do you find points on curves? Plug in stuff. What do you got, Chris?
1 minus 3.
That's exactly what I would have done. I would have said, well, if I can't plug in 0, fine, plug in 1. Oh, well, if x is 1, then what's y? Okay. This is like mine, similar to. This is an example of an x and a y, true? An x and a y that I know is on that graph. Okay. So if this x, y is on the graph and there is a symmetry, I can test. This is where it gets a little funny. Let's see if it makes sense. I'm going to test what if, for x-axis symmetry, what if x stays the same and y flips? True. For y-axis symmetry, what if x flips but y stays the same? And then for origin symmetry, what if x flips and y flips? How will we test it? Yesterday, how do we test if something is a solution? Plug it in and look for what kind of statement? So therefore I can plug in and say, hey, does 3 equal 1 minus 4? Sorry, 1 squared minus 4, which is 1 minus 4. Does 3 equal 1 minus 4? No. 3 does not equal negative 3. So that one's out. Does negative 3 equal negative 1 squared minus 4? Yes. PEMDAS, that'd be a 1. 1 minus 4 is negative 3. Yes. Okay, that's a winner. Last one, does 3 equal negative 1 squared minus 4? 3, negative 3? No. Does this come up with the same exact solution as that? Yeah. But if you like numbers better, you just have to do the extra action step of finding a point on the curve and then thinking, keep the x opposite y, keep the y opposite x, opposite them both, and just seeing which one's what. Okay? For most of us, we probably want to get to the place where the general works because the specific, it's kind of like, we'd rather just have, in most of math, right, a general equation that we can use over and over. Specific, it just depends on the case that we have. But there you go. I do want to show you guys really quickly that table that is in the book. It tells you what to do as far as, hey, plug in y with a negative y. Hey, plug in x with a negative x. Hey, plug in x with a negative x and y with a negative y. That's a lot of words. I don't know, kind of like my way of summarizing it. And it does the exact same procedure as I do. If you guys want to check it out in the book, please feel free when you're doing homework to do so. We only have one last thing to figure out. Let's start with the equation. I think it's the last thing, right? Yeah. Circles. Once you get that equation down, I'm going to try to tie together circles with symmetry. I don't know if the book does it or not. I'm trying to tie together circles with symmetry. Let me get rid of all this count stuff. As you guys finish writing out its standard form equation of the circle, how do you pop that? The command strips went done. Or command strips. Okay, anyway, coming back. Question. What kind of symmetry does a circle centered at the origin 0, 0 with a radius of I don't care any? What kind of symmetry does it have? Just think about it. I've heard complete, I've heard all, I've heard some, I've heard origin. I'm going to do, I don't know, let's do a radius of 2. Just have fun. And then somewhat symmetric. Okay, so as I have my circle, question, does it have y-axis symmetry? Yeah, fold the y copies, cool. Does it have x-axis symmetry? Fold the x copies, cool. Does it have origin symmetry? Fold, load copy. Yeah. What's there is there, what's there is there, what's there is there. So therefore, how many symmetries does this have? 3. All. It has x-axis and y-axis and origin. So my question is, how many symmetries can any function have?
3.
Up to 3. Could have 1, could have 2, could have 3. Wait, could have none. Right? What would be a graph that has no symmetry? At least it doesn't have any of those 3 types of symmetry. Is it symmetric? Yes. But about the x? No. About the y? Mm-mm. About the origin? It doesn't have the 3 basic types of symmetry. You would have to redefine an extra line way out here, call him, the axis of symmetry, and make a special name. Anyway, circles have all 3 symmetry, that's nifty. However, even circles don't have to have any of the 3 main types of symmetry if they are shifted, and if they shift, we'll see that shift in there being an h and k that are not 0. The center of the circle will be at hk. I'm going to do it random. H will be the x, k will be the y, and then the circle will go ahead and go out from there, whatever, of course. What does R stand for? Radius. Whatever R is. Remember real quick that radius is being squared, so if you see a number and you're trying to find the radius, you have to square root. But as you guys know, our book digs a little deeper in each of these concepts. So, what would you have to do to answer this final exam?
It's upstairs.
What would you have to do to answer this final? Yeah, remember I said you could be 2 minutes early? How would I answer? Pause. I know we got a little distracted. What goes in the H spot? X minus negative 1, which is x plus 1. What goes in the K spot?
2.
What goes in the R spot? So how do we find the radius? Solve using the distance formula. Bye, kids. Have fun with homework. It's due tomorrow. enough, because I'm on my final page.